Okay, so this is the extra video for senior cycle from the sequences series. So we'll just give another example going back to sequences formed from shapes. This is from the book, it's on page 281. And it tells us that we have some designs. They're made by arranging counters in L shapes. So there's design 1, 2, 3, 4, 5, and so on. So complete the table for the designs. So the design number is n is 1, 2, 3, 4, 5, and the number of counters, we can count the counters and put it into the table. Now, I can't recall, but maybe you were given 3, and you kind of worked out that going from 1 counter to 3 was 2, and going from 3 to 5 was 2, and you complete the table by adding the 5, the 7, the 9, the additional bits of information. Okay, so we're asked then how many, bear with me, how many counters for the 15th design. So when n is 15, what's the how many counters? What's the value of the term? Okay, t15. Okay, so the way to approach this is we need to generate the nth term rule for that sequence. Okay, so how do we do that? Okay, so we know that we've 1, 3, 5, 7, 9, and we know that the what's going on, the term rule there is the addition of 2. So we always start by saying Tn equals this value times n, okay, whatever the term rule is. So if that's the case, what's T1? Well, T1 is 2 by n is 1 is 2. But our first term is 1, so we need to, what do we do to change this 2 into a 1? We take away 1. So that means it's not actually Tn is equal to 2n, it's equal to the nth term rule is Tn is equal to 2n minus 1. Okay, so the 15th term, T is 15, n is 15, it must be 29 counters for the 15th design. Now, what design uses 99 counters? Well, which design is it? Is it the 50th, the 51st? What is it? What's its n value? What's its position? Well, we're told that it's the value of the term in that position is 99. So 99 must be equal to 2n minus 1. So that means 100 is equal to 2n. So the 50th design has 99 counters. Can we make a design with 40 counters? Okay, so can we make a design with 40 counters? Well, that's telling us that there is a term in the sequence equal to 40. Is that possible? Well, let's see. We'll let that 40 equal to, that's our Tn value, and we're looking to find what term is it going to be. Not what term, what position it's going to be. So we let 40 equal to 2n minus 1, so that means 39 is equal to 2n. So that's saying that the position is at 20 and a half, and that doesn't make sense really. It has to be a whole number, so no, you can't have a design with 40 counters, because there's no position for 40 in the term 40 in this sequence. So now we're going to look at arithmetic sequences. So let's consider the sequence 2, 4, 6, 8, 10. Each term is found by adding 2 to the preceding term. It's obvious enough. This is an arithmetic sequence because any term after the first can be found by adding a fixed number to the term before it. Okay, so the fixed number that we're adding to the term before it is 2. Okay, so if we add 2 to 2, we get 4. If we add 2 to the number before, we get 6, and so on. Okay. The first term in this series, we call it we give it the notation A, and the fixed number, we call that in maths the common difference, and we give that the notation D. Okay, and it's really it's an important little formula here. It will come up at some stage. The common difference D is equal to any term minus its previous term. Any term 10 minus 8, common difference is 2. Okay, so how do we find the nth term or generate the nth term rule of an arithmetic sequence? Well, this is the formula that we use. Okay, the nth term rule for an arithmetic sequence is always equal to the first term plus n minus 1 times the common difference. Okay. So let's find, for the arithmetic sequence, let's find the nth term rule. So it's 3, 8, 13. Okay. So we know the first term, let's find a, sorry. A is equal to 3. D is equal to any term, 8 minus the previous is equal to 5. So what is the nth term rule? Well, we plug those values into here, and we'll get Tn equals 3 plus n minus 1 times 5. And so what are we doing there? Okay, yeah, so we'll multiply that out. So 5 by n is 5n, 5 by minus 1 is minus 5, 3 minus 5 is minus 2. So the term, nth term rule for this arithmetic sequence is given by that rule there. Okay, and if we're asked to find then what the value of the 20th term is, n is 20, plug it in, it's 98. Another example, find the nth term rule of the arithmetic sequence 7, 10, 13, 16. So A is 7, D is 10 minus 7, any minus its previous is 3. So use the formula here, plug it in, Tn equals 3n plus 4 for that sequence. Which term of the sequence is equal to 97? So what what value of n, where is it that it's equal, the term value is 97. So Tn is 97, but Tn is also equal to 3n plus 4. So 97 equals 3n plus 4. So solve for n. It's the 31st term, has a term value of 97. And then show that 168 is not a term of the sequence. So Tn equals 168. So you equate 168 equals 3n plus 4. Find the value of n, and you'll see that n is 54 and 2/3. It's not a whole number, so you know you can't land on a term that's a fraction. It has to be the first term, the second term, not the second and a half term. Now, looking at arithmetic sequences in another way, how do we find the values of a and d? So let's say we're told that the fourth term of a sequence is 11 and the ninth term is 21. Find a and d, and then find t50. Okay. Well, we need to generate some simultaneous equations. Okay, so we have the formula Tn is equal to a plus n minus 1 by d. So what's T4? Well, T4 means we plug in 4 for n there, and we'll generate the fact that T4 is equal to a plus 3d, but we also know that T4 is equal to 11, so we'll equate it to 11 and we'll generate this equation here. A plus 3d equals 11, first equation. T9, we'll plug in 9 into our original, into this formula here. We get a plus 8d, and that's all equal to 21 because we know that from here. So that generates a second equation, which we'll solve simultaneously by changing the sign and adding. We get d is equal to 2, plug that back in there, and we get a is equal to 5. So here's an interesting example here. If x plus 1, 2x minus 2, and 2x plus 1 are three consecutive terms of an arithmetic sequence, find x, find Tn, and T100. Okay. Well, we know, first of all, we'll just state that the first term a is equal to x plus 1. Okay? We can also work out that d, a is equal to x plus 1, that d is equal to the difference, the common difference. So it's 2x minus 2 minus x plus 1. And be careful always of the minus sign there. Okay, so that's 2x minus 2 minus x minus 1 equals x minus 3. So d is equal to x minus 3. But there's, that probably, I'm saying here that won't work. There's a quicker way to get to the solution. It's an arithmetic sequence. So if we have T1, T2, T3, T4, T2 minus T1 is the common difference, and T3 minus T2 is the common difference, and they're the same, okay? So it's fair to say that T2 minus T1 is equal to T3 minus T2. And that's what we've said here, okay? So if we plug in our T2 is 2x minus 2, and our T1 minus x plus 1, and plug in our other values here, then this is what we're generating here, and we end up with x is equal to 6. Okay, so we've found x here. I'm just trying to expand out. It's a bit small. I appreciate it's a bit small. So that's actually what's happening in here. So x is equal to 6. We know what a is. We know what d is because we worked that out earlier, and we can plug our x value in now. So we can see that d is 3. 6 minus 3 is 3. And if that's the case, then our Tn is equal to 3n plus 4. So T 100 is equal to 304.